So today we're going to talk about one of my all-time favorite things, and that's partial fraction decomposition. And I love this stuff because it combines two of my favorite things in math, fractions and integration. So it's like the best. So I have four rational functions up on the screen, right? You're trying to integrate all of them. So when it comes to rational fractions, there's a lot of different techniques that you could take advantage of. And you really have to be very savvy and kind of have a lot of intuition because you solve a lot of problems to start figuring out which method is going to work, right? So we always want to try u substitution first if we can. So if we look at integral a, right, 1 over x plus 2, that one's a really basic u sub, right? Because I would make u equal to x plus 2, then my du just becomes dx, right? So that's going to end up being natural log of x plus 2. So that's really easy. I'm not even going to bother going through and integrating this, right? And then b, right, again, you always want to try u sub first if you can. So if I make the u equal to the denominator, which is always your best bet with a rational expression, right, my du is equal to 2x plus 6 dx. And if I take half of that, right, half of my du would equal x plus 3 dx, which is exactly what I have, right? So this would become the integral of 1/2 du over u, right? That one, I should probably write this out. That was an awful integral symbol. Okay, so I get for trying to hold my cup of coffee while I'm doing this, right? That's just dx over x, not dx, du over u, right? So both of those are going to end up being natural logs. Really simple, pretty straightforward. Right, when we get down to something like c, we have a polynomial, we have a quadratic in the denominator, and it's not factorable, and there's no x to help it balance out in the top, meaning that if we take a u substitution with just the quadratic as is, we don't have anything to balance our du with, right? We're not going to be able to just get rid of dx very easily and make it less complicated to integrate. And it's not factorable, so in that case, it's probably a complete the square. So if I complete the square real fast, just going to skip some steps here just for demonstration purposes. Right, I would add 9 to both sides because 6 over 2 squared is 3 squared. So that's y minus 1. Right, so if I substitute this into the denominator, that actually just becomes an arctan integral, right? Because it's a variable squared plus a number being that you can write as a square, right? 1 squared is 1, right? So that's going to be a basic arctan, right? You just got to do a little bit of u substitution to make sure you make it all fit correctly, right? But when I go over to something like d, if I complete the square, right, because u sub's not going to work because it's not like a and b where it's got an x or something in the numerator that's going to balance out the du part, right? If I quick complete the square by moving the 7 over, I know I'm going to add 9 to both sides because of the last problem. Right, but now it's a minus sign in between. So that doesn't fit anything that we know right now because it's got to be x squared plus something, like plus a number to fit arctan, and we still can't use a u substitution because it's not going to balance out with anything in the top and make it where it's a format that we actually know. So this is actually where partial fractions is going to come into place, right? So this doesn't work, but what we can do with this rational expression is we can factor the denominator, and if you can factor the denominator in a rational expression and it's like a basic u sub's not going to work, that's kind of what tells you that you want to use partial fractions. So I'm going to actually use this problem to kind of show you how to do partial fractions. So some things that you just want to be aware of. Partial fractions are only used for a couple of reasons. So partial fractions, some kind of keys for when you want to use them. Right, it's got to be a rational expression inside your integral, meaning it's a fraction. And your denominator needs to be factorable. So your denominator can be factored. And if we're looking at it overall as a rational expression, you specifically only want to use this when the degree of the denominator is greater than the degree of the numerator. So higher power in denominator, or higher exponent in the denominator. If not, if you have an equal power in the numerator, or if you have a higher power in the numerator, that signifies that you want to use long division or synthetic division first to help kind of break apart your expression, and then you still might have to use partial fractions. So there's really 3 cases for partial fractions. I'm only going to cover the first case in this video, which is pretty basic. So there's 3 total cases. I'll write that down, and we're going to go over case 1 today. And by cases, I mean there's 3 basic scenarios that kind of have different solving techniques in them and how you set them up. But case 1 is the most basic. So when we're using case 1, I wish I could write today. Case number 1. That's when our denominator factors into distinct linear factors. So what I mean by that is you can factor the denominator, and all of the factors that it breaks down into are linear groups, right? So there's only powers of 1, and they're distinct, meaning that there's no repeated groups. They're all different, which is exactly what that example that I wrote up here, example D, is going to show us. So we're going to use that example to kind of demonstrate how to use this. So kind of move that down, space it out a little bit better. Okay, so our example here is we're going to go ahead and integrate the expression I wrote down above. Okay, so the first thing you want to do is factor it. I actually want to rearrange this because I tend to write big. Okay, so we're going to factor this. So that's going to be x plus 7 and x minus 1. I'm going to leave my dx in the numerator. So then this is a case where you kind of want to go off to the side or go off to a scratch piece of paper and do your algebra manipulation off to the side, like outside of the integral, otherwise it gets super complicated. So this is kind of, so when you have like multiple terms or whatever, and like you're in an algebra class or something, and you're simplifying an expression that has fractions in it, right? Often we tell you to combine all the like terms, which means that you would like add all of the fractions together. Partial fraction decomposition means you're undoing that. You're taking one fraction and you're decomposing it into the sum of many fractions. So in this case, right, we have, right, there's really a 1 in the top here. So I'm going to go off to the side for my scratch work and say, okay, well, this is 1 over x plus 7 times x minus 1 here, right? I'm going to even ignore that. And I want to break that down into the sum of 2 fractions. So I want one fraction to have a denominator of x plus 7 and one to have a denominator of x minus 1. And if you think about when you learned how to add rational expressions back in Algebra 2, right, you would start with something that looks like the problem on the right, and you would end up making the common denominator by multiplying the 2 unlike denominators together, which would give you the denominator on the left. So in the numerators for these are always going to be 1 degree less than the power in the denominator. So right now I have a degree of 1 in the denominator, which means my degree of my numerators would be 0, which means there's just a constant in the numerator. So I'm going to represent those by A and B. So A and B are just numbers, and they're representing the numbers that are going to be in the tops of these fractions. So then I'm going to kind of undo this because we need to figure out what A and B are. So eventually we're going to set up a system of equations in order to help us solve. So, okay, if I have 1 over x plus 7 times x minus 1, if I were to add these 2 fractions together on the right, which I'm going to need to do in order to figure out what A and B are, right, I would really just cross multiply the denominators. I'd say, okay, well, this is A times x minus 1 over x plus 7 times x minus 1 plus b times the opposite denominator over our common denominator. So since the denominators are now all the same, I can kind of ignore them, right? Because the denominators would cancel out if I multiplied both sides of my equation by x plus 7 and x minus 1. So I'm just going to ignore them and write 1 is equal to a times x minus 1 plus b times x plus 7. So now you might be thinking, how am I supposed to solve for a and b when there's 3 variables in this equation, right? We got a, b, and an x. So the easiest way to actually solve these is to use different x values and then set up a system from there. If you need to. So I like to work smarter, not harder, right? So I'm going to plug in numbers that zeroes out part of the equation. So I'm going to start by plugging in x of 1. And when I do that, right, the 1 on the left-hand side says 1. And then I would have a times 1 minus 1 is 0, which is why I did it, plus b times 1 plus 7 is 8. Okay, well that term cancels out then. We get 1 is equal to 8b. So I get 1/8 is equal to b. And then if I wanted to cancel out the b term, I need to plug in -7. So if I plug in -7, I get 1 equals a times -8 plus b times 0. So I'm going to get 1 equals a -8a. So -1/8 is equal to a. So what I'm going to do with all of that algebra that we just did off to the side is I'm going to go back over to this and I'm going to break this apart. So my first fraction here, right, with a, right, a is equal to -1/8 and b is equal to +1/8. So I'm just going to write that expression into my integral. So I'm going to get -1/8 over x plus 7 plus +1/8 over x minus 1 dx. And then I'm going to break this up. So I'm going to bring the -1/8 out and then leave this as dx over x plus 7 plus bring the 1/8 out of my second integral, and I'm going to put the dx in the numerator. So now because we wrote it like this, right, we can actually do kind of two different u subs here. Use a different color. So in this case, u would be x plus 7, so then du is just equal to dx. And I'll use a different letter over here. I don't know, I'll use w. W is equal to x minus 1, so then dw is also equal to dx. So if we're being like really particular about showing all the work, we're getting -1/8 times du over u plus 1/8 times the integral of dw over w, right? Making our replacements, our substitutions. Well, that becomes -1/8 times the natural log of the absolute value of u plus +1/8 times the natural log of the absolute value of w, all plus c. And then we're just going to substitute back in. So this is -1/8 natural log of x plus 7 plus 1/8 times the natural log of x minus 1, all plus c. And the more you do partial fractions, the more you're going to see that the natural log comes out a lot in these. So if you're doing partial fractions and your answer is not like all natural logs, you're probably doing it wrong. Okay. So I'm going to throw another one up on the screen and I'm just going to take a quick pause. So I would pause the video if you want to and try this one on your own. And then unpause and watch me do it and check your work against what I do. So I want you guys to try and integrate 4x plus 1 over x squared minus 5x plus 6 dx. So it's still case 1, but go ahead, pause the video now, see if you can solve this on your own, and then unpause to watch me solve it. Okay, so I'm just going to go ahead and start this over off to the side. do it in purple this time. So I have 4x plus 1 and factors the bottom, x minus 2 and x minus 3. Okay. So I want to break this into two fractions. So I'm going to put a over x minus 2 and then b over x plus minus 3. Yours might be in a different order. That just means that your a and b values are going to be backwards of mine, and that's totally fine. So if I were to make this into one big equation, normally I skip this step when I'm doing it like just for solving problems on my own. I don't show this step, but I'm going to show it for you guys. All right, so making my fractions have a common denominator. And then once they all have the same denominator, I can ignore the denominators. Oops, it would help if I actually wrote everything in here. There we go. Okay, so then I'm going to cancel out the b's first. So b is being multiplied by x minus 2. So if I plug in positive 2, that part's going to cancel out. So if I plug in positive 2 on the left of 4x plus 1, that's going to be 4 times 2 plus 1. So 9 equals a times negative 1 plus b times 0. So those are going to go away. So 9 is equal to negative a, which means that a is equal to negative 9. And then I'm going to plug in positive 3 now to cancel out the a's. So 4 times 3 plus 1 is 13. I'm going to get a times 0 plus b times 1, right? So that just means that 13 is equal to b. So then I'm going to go ahead and go back over to my integral and rewrite the inside to be negative 9 over x minus 2 plus 13 over x minus 3. So I'm going to write this as two separate integrals first. You just want to be careful when you're going to write your integrals as the sum of two fractions instead of the original one, that you put your a and b value over the same denominator that you had in your setup, because if you flip them, then your answer is going to be wrong. So I'm not going to do the full u substitution here, right? Because if the u is equal to x minus 2, the du is just dx. Okay, so that integral is going to become du over u. So I know that's going to be a natural log. It's going to be negative 9 natural log of the denominator. And then same thing over here because it's a linear term, right? If I make this w equals x minus 3, my dw would equal dx. So that's just going to be dw over w. So again, natural log. So 13 times the natural log of the denominator, all plus c. And I can do that here because I have linear binomials in the denominator and they have coefficients of 1 next to the x's. So I don't have to worry about like a du happening, right? So like